Hello everyone, welcome to this NPTEL course on computational process design. In today's session what we are going to see is we will be looking at simulation for process flowsheet. So remember in the initial sessions we have seen the simulation of the process flowsheet by using linear mass and energy balance, isn't it? So linear mass and energy balance gives the approximate calculations, but for final cost calculation we require more accurate uh, simulation and calculation of the process flow sheet. So that is what we are going to look at in little bit more detail in today's session. So if you look at the process simulation modes, typically the process simulation can be performed by using two methods. One is the modular approach and the second one is the equation oriented approach. So in modular approach, usually what we do is, in modular approach, each of these equipments, each of these units which are there in the process flow sheet, we solve these units individually, and then we try to connect these with respect to the entire flow sheet, and based on that then we do the iterative calculation till we get the uh, all the assumed values same as the output values. Okay. So in modular approach is popular for flowsheet design and analysis with detailed process models, but require nested convergence of several calculation loops, making it more robust for non-linear process calculations. So clearly, if there are several non-linear equations are there with respect to individual units, in that case, approximating these non-linear equations using a linear equations, as we have seen in the initial material energy balance session, that is going to give you some error, isn't it? So whenever we have such non-linear models, the better approach is to use a modular process simulation approach, in which we can solve all these non-linear equations corresponding to individual units directly, and then we will be combining it together. Okay. So in the modular approach, convergence involves solving physical property equations at the lowest level, unit operations at the middle level, and recycle streams in the flow sheet. So you can see that there are three levels in the modular approach. So how we can calculate the properties, that will be the lowest level. Then intermediate level we look at solving the individual units, and at the highest level then we combine everything with respect to the sequence of the units those are present in the flow sheet, and then we try to see whether the inputs for different units which we have assumed in the starting is matching with the predicted values or not. So modular approach input output structure can make it inflexible to flow sheet design specification, often necessitating additional calculations loops to meet the requirements. As I said that, remember in a modular approach we start with some assumed values of input, isn't it? And then we do all the calculation with respect to individual units, isn't it? And clearly these assumed values should be matching finally when we are combining all the units, isn't it? So there are several iterations are required, there are several loops are required, isn't it? So the equation oriented approach, if you look at in contrast with the modular approach, in equation oriented approach what we do is we take all the equations with respect to different units and we solve all these equations in one go. So in equation oriented approach, flowsheet equations are solved simultaneously, leading to more efficient solutions with less computational effort compared to the modular approach. The problem with equation oriented approach is primarily the convergence. So see, if there are several non-linear equations are there, typically what we do is we use the non-linear equation solvers, and all the non-linear equation solvers require a starting values for the problem, isn't it? So typically the convergence depends on what starting values we are using, how accurately how efficiently the non-linear equation solver is solving the problem. That is also important. Sometimes these non-linear equation solvers can diverge also. Okay. So equation oriented mode allows arbitrary design specifications without additional calculation loops, but require large scale non-linear equation solver for the entire flow sheet and careful problem initialization for successful solution. Let us take a very simple example. This is a commonly used example in several textbooks. So this particular flow sheet is referred as Williams and Otto flow sheet. So this particular process is given by Williams and Otto in 1960s. So in this particular flow sheet, you can see that there are different units are there. There is a reactor, then there is a heat exchanger, then there is a decanter and the distillation column. So in the reactor, you can see that the reactant A and reactant B are charged to the reactor, uh, and the recycled stream is also charged to the reactor. And in the reactor, three reactions are occurring. A plus B is giving C, C plus B is giving P plus E, and P plus C is giving G. So in these different species, you can see that the C is an intermediate substance, P is a primary product, E is a secondary product, and G is a oily waste byproduct which we have to remove. So the entire effluent which is coming from the reactor then charged to the heat exchanger, where the heat is removed from the effluent, and this cooled effluent is then charged to the decanter. In the decanter, you can see that the waste byproduct G is completely removed, and the other remaining products are then charged to the distillation column, where the desired product P is separated as a uh, dis distillate, whereas the other products are removed at the bottom. Again, in this case, what we are assuming that uh, the bottom product basically makes a azeotropic mixture, and because of that, around 10% of product P with respect to the component E is getting uh, uh, eliminated, is getting removed in the bottom. So it is not complete 100% separation. 10% product of that of E is forming the azeotropic mixture with the bottom product. Okay. So both C and E holds a value as a fuel commodities, whereas G requires disposal, and therefore there is a cost incurred. The plant comprises a reactor, heat exchanger, cooling reactor effluents, a decanter to separate the waste product G from the reactants and other products, and distillation column for product P separation. Okay. So now let us look at the model for each of these units which are there in the flow sheet, and then we will see how this can be combined in modular and the equation oriented approach. So if you look at the reactor, in the reactor you can see that F2 is the feed rate of B, F1 is the feed rate of A, FR is the feed rate of the recycle stream, and F effluent is the whatever the product stream coming out from the reactor. In this case, if we write the mass balance for individual components, we can write down the mass balance for the component A. So uh, mass flow rate of component A in the effluent will be given by Fa effluent, and that is given as F1A plus F1A plus FRA minus K1 XA XB V into rho. So in this case, you can see that F1A is nothing but what? F1A is nothing but the mass flow rate of A uh, uh, given as a input through a stream 1 here, this F1A. FRA is nothing but the mass flow rate of A which is present in the recycled stream. Okay, so these are nothing but the component A input to the reactor, and remember, in this case, A is getting reacted with B to produce C. So clearly A is getting consumed by the reaction. So the consumption of the A is also represented through the second term, which is nothing but minus K1 XA XB V into rho. Here V is the volume of the reactor, and rho is the density of uh, the reactants present in the reactor. Okay. So in this case, you can see that this gives us uh, the mass flow rate of A coming out from the effluent. Similarly, we can write down the mass balance for the mass flow rate of the component B in the effluent. That will be given by F2B plus FRB minus K1XA plus K2XC into XB V rho. So here you can see that F2B is nothing but the component B is added to the reactor through this stream F2. FRB is nothing but the amount of B present in the recycled stream. K1 XA XB is nothing but the uh, uh, B is getting consumed by reaction 1. Similarly, K2 XC is nothing but the B is getting consumed by reaction 2 and multiplied by volume and density. Similarly, we can write down the mass balance for the component C. So Fc effluent is nothing but the mass flow rate of the component C coming out in the effluent, that will be given as FRC. So FRC, remember in this case the fresh feed is only for A and B, there is no fresh feed of C is coming in. So FRC is the only input for the C, component C. So in this case component C is primarily coming through the recycled stream, plus uh, remember in this case C is getting produced by reaction 1, C is getting consumed by reaction 2 and C is getting consumed by reaction 3. So all these are represented using this entire term which is there in the bracket. Also component E, if we look at the component E, in this case the mass balance for the component E can be written as Fc. This is E, maybe I'll just correct it. So in this case you can see that this is for component E. So you can see that the mass balance for the component E can be written as FRE plus 2 K2 XB XC 0. Here you can see that component E is getting produced only by the second reaction, and therefore only second reaction is coming into the picture here. One more correction is required here, that I'll just do it. So in this case this will be K2, this will be K2. Okay, so similarly we can write down the component balance for the component P. Component P is getting produced by second reaction and it is getting consumed by the third reaction, so that is also represented using this mass balance. And finally the last equation corresponds to the mass balance for the component G, where you can see that the G which is coming through a recycle stream is taken as a input to the reactor, and then G is getting produced by a third reaction. So that is what is represented here in the third reaction. Okay. So clearly here in this entire material balance equations, you can see that Fi represents the mass flow rate of the component I, Xi represents the weight fraction of the component I, and Kj represents the rate constant for the respective reactions. Again we can write down the expressions for the K1, K2, K3 in terms of the in the Arrhenius form, because then that will give us the how the rate constants are related to the temperature. That effect can be built in through these Arrhenius equations. Now let's move to the another unit. Remember, after reactor the next unit which is there in the process flow sheet, if you look at the next unit, is a heat exchanger. So we will be looking at the equations with respect to the heat exchanger. In the heat exchanger so heat exchanger actually facilitates the exchange of heat between the streams. So you can see that the hot product stream coming out from the reactor is cooled down in the heat exchanger. So you can see that if you look at the heat balance, so heat balance, if you consider the heat balance here, the heat balance is nothing but the heat lost by uh, the uh, the effluent will be nothing but the heat gained by the coolant which is flowing through the heat exchanger. Okay, again if you look at the mass balance equations with respect to the heat exchanger, so there is no change in the mass flow rate of the different components is taking place, and therefore f Fjex, which is nothing but the mass flow rate of different component J coming out from the exchanger, is exactly same as Fj EFF. So the mass flow rate of different components is exactly same as the mass flow rate of different components which are coming in through a effluent stream. So the equation signify that the mass flow rate of each component remains constant through the heat exchanger, indicating a simple exchange of material without any change in composition or mass within the unit. The heat exchanger model serves the purpose of the transferring heat between the incoming and outgoing streams without altering the mass balance of the components. That is what we have said. So there is no change in the mass balance takes place, only the heat is lost by the hot stream, and the same amount of heat is gained by the coolant which is flowing through the heat exchanger. The next unit is a decanter. So in decanter you can see that the decanter unit which is there in the process flow sheet is primarily used to remove the waste byproduct G. So uh, the decanter assumes a perfect separation between the component G and the other components, simplifying the separation process within the unit. The equations for the decanter unit are as follows. So you can see that in this case, if you look at the mass flow rate of all the components except G are same as whatever we have obtained after the heat exchanger. So that is why FDI is same as FJEX. So you can see that the mass flow rate of all the components are same in this case. Okay. Now this will be FJ. I'll just correct. So this will be J. Okay. So again you can see that FDG is equals to 0. So you can see that whatever the product is getting separated at the top from the decanter, it will not have any uh, uh, it will not have the byproduct G, because this byproduct G is getting separated at the bottom as a waste product. So you can see that FG waste will be equals to FG EX. So that is nothing but whatever is the input G to the decanter, the same amount will be removed here at the bottom, and all other components other than G, these will be negligible. So therefore Fj waste is equals to 0. So you can see that at the bottom Fj waste, where J is varying as A, B, C, E, P, so all other components will not be there in the bottom. So these equations indicate that the mass flow rate of components A, B, C, E and P remains unchanged, while component G is completely separated within the decanter unit. Now the last unit is distillation column. So the distillation column unit in the process flow sheet depicted in the figure is designated to separate the product P as overhead product, whereas some amount of product P will be retained in the bottom because of the azeotrope formation. Again, the distillation column assumes a pure separation of product P at overhead and accounts for the retention of the portion of the product below the column due to azeotropic formation. So if you look at the equations here, you can see that if you look at the equations at the bottom, equations with respect to the mass flow rate at the bottom. So uh, Fi bottom here is nothing but Fdj. So whatever the components are coming from the decanter unit, the same mass flow rate will be there for different components A, B, C, E at the bottom, isn't it? Again, Fj product equals to 0. So whatever the product is taken out as a distillate, you can see that at the distillate all these component J's will be absent, whereas at the bottom we will have this product P will be 0.1 multiplied by the mass flow rate of the component E. That is what the condition we have started with, isn't it, in the problem statement. So due to azeotropic formation, some product equivalent to 10% of the mass flow rate of E remains in the bottom. So equivalent to 10% of FDE of uh, uh, product P will be in the bottom, whereas the other remaining part will be separated with the 100% purity as a top product. So that is what is represented. You can see that FP product, this is nothing but the mass flow rate of the desired product P separated at the distillate, that is given as FDP minus 0.1 FDE. So FDP is nothing but the mass flow rate of the product P entering in the distillation column, minus 0.1 FDE is nothing but the equivalent amount of product which will remain in the bottom. So that is subtracted. So remaining will be separated at the distillate. So you can see that these are the 4 units. Specifically this simple flow sheet is taken because then you will appreciate how these are solved in the modular as well as the equation oriented approach. So In addition to this, remember in the process flow sheet, if we look at whatever the bottom product coming out, uh, this will be again given as a input to the splitter, and in the splitter some part will be purged and the remaining part will be recycled back. And this is very very important because we wanted to maintain a uh, specific concentration of different components in the inlet, isn't it? So that is what we have seen earlier also when we have started looking at the mass and energy balance with a linear mass and energy balance with linear equations in the initial sessions, isn't it? So there also we have seen a similar case. So in this case, finally the bottom product coming out from the distillation column will be charged to the splitter unit, where some part will be separated as a purge and the remaining will be recycled back. So the flow splitter unit in the process flow sheet as depicted in figure is designated to split the incoming flow into two separate streams based on the specific split fraction. And this split fraction is very very important. This split fraction we have to decide based on what concentration we wanted to maintain in the recycle stream. Okay, so the flow splitter unit divides the incoming flow into two streams, facilitating the distribution of components according to the defined split ratio. So in this case, fj purge is given as eta into f bottom j. So here eta is nothing but the split fraction. So you can see that some specific specific fraction of the f bottom will be separated as a purge, and the remaining 1 minus eta into fj bottom, this much stream is recycled back. The flow splitter unit plays a crucial role in the process flow sheet by allowing for the controlled splitting of flows, which is essential for directing components to different parts of the process based on the desired distribution. So this is what we were discussing, isn't it? In order to maintain the concentration of different components in the recycle stream, isn't it? That is what we are giving as a input to the reactor. In order to maintain that at a particular value, we need to have a desired split fraction. Here we have to remove some part as a purge and the remaining has to be recycled back. Now coming back to the modular mode, remember we said that this particular flow sheet we will discuss how this particular flow sheet can be solved using modular mode. So the modular mode in process simulation involves segregating process equations within individual units and executing these units sequentially. So you can see that if I look at the entire flow sheet here, there are uh, there are in fact five units are there: reactor, heat exchanger, decanter, distillation column and splitter. There are five units are there, and all these five units we have to solve sequentially one after another. Okay, so if you look at the modular approach, the model corresponding to each of these units, we are calling it as a model for the individual unit operations. Okay, again in each of these unit operations we need to calculate different properties, isn't it? Different thermodynamic properties we have to calculate. So that comes in the level 3, isn't it? Lowest level in the modular approach, isn't it? And in addition to that, remember when we are solving it sequentially, we start with the assumption that what will be the concentration of different species in the recycle stream, that fraction we start we assume initially, isn't it? And based on that we are sequentially solving all these five units, and based on that then finally again we calculate what is the concentration of different components which are present in the recycle stream. And if these are not matching, in that case what we have to do is we have to do this simulation repeatedly in a iterative manner till we match all these calculations. So that is what is done in the modular approach. Okay, so in this, the process equations are solved in a step by step manner, with each unit being solved independently before moving on to the next unit. The process in the modular mode is structured based on the flow sheet topology. Remember whatever the flow sheet is given and how different units are arranged sequentially, the same sequence is followed in a modular approach. where units such as reactor, heat exchanger, decanter, distillation column and splitter are executed in a specific sequence with defined input streams. So you can see that if we assume what are the concentration of different streams in the uh, recycle stream, based on that we can solve the mass and energy balance for the reactor, isn't it? Based on that we will get what will be the values with respect to the input stream which is there for the heat exchanger, isn't it? So you can see that if we assume the uh, concentration of different components in the recycle stream, we know F2B, we know FAB, we can solve this reactor and we can obtain what are the values in the effluent, isn't it? That once we get what are the values in the effluent, what are the different mass fractions or mass flow rates of different components in the effluent, what is the temperature of the effluent, based on that we can give that input to the heat exchanger, and heat exchanger based on this input then how much amount of heat is removed, based on that the temperature will be changed here and mass flow rate will remain the same, isn't it? That is what we said. Once we have done that, we will get the mass flow rate of different components in the fx stream, isn't it? And that will be given as a input to the decanter, and based on this input then we are going to solve the equations with respect to decanter, isn't it? Here also different in each of these unit you can see that the different thermodynamic property one has to calculate, isn't it? So that we can calculate based on the temperature and pressure values whatever we are having along with the mass flow rate. So once we solve the equations for the decanter, we will get the output variables coming out from the decanter, which will be given as a input variables to the distillation column, and then we can solve the model equation with respect to the distillation column. Based on that we will get the value of the variable f bottom, different components those are present in the f bottom. Based on that we can solve the equations with respect to the splitter, and finally once we solve the expression for the splitter, we will be getting what will be the concentration of different components in the recycle stream, and that we are going to check with respect to whatever we have assumed in the starting. If these are not matching, then we have to solve this entire calculation repeatedly till we get both these values, starting values and the predicted values same. Till that point we have to perform the iterations. So you can see that the initialization process in the modular mode involves guessing initial flow rates for certain streams and iteratively updating these values to achieve convergence in the simulation. Okay. The modular mode simplifies the simulation process by encapsulating unit models as procedures, enabling the evaluation of the output streams based on the input stream and design parameters. So you can see that individual, remember in this modular mode, we are solving individual units sequentially one after another. So solution of these individual units we can consider as different steps in the solution procedure. That is what is written here. If you look at the entire methodology is represented schematically here, you can see that we are solving the unit operation models. For unit operation models we require different properties, so we will be solving the physical property models based on the thermodynamics or different empirical rules. Based on that we will be obtaining the physical properties. These physical properties at the given condition we are going to use at different unit operations. Then we are going to solve the non-linear model equations corresponding to each of these units, and once we have solved that, then we are going to combine all these unit operation solutions with respect to how sequentially different units are arranged in a flowsheet topology. In fact, this unit operation we have to, whenever we are solving this unit operation models, you can see that the output of one is given as an input to the other. So in fact there is a back and forth information exchange between flowsheet topology and unit operation models, and same thing is happening with respect to all these, isn't it? So there is a back and forth calculation of the physical properties depending on the change in the temperature, pressure, etc., isn't it? Okay. So in a modular mode, you can see that if you look at the hierarchy in the modular mode, hierarchical structure of the simulation process involves three main levels of the operation, and these three main levels we have shown here, isn't it? So the lower level is the physical property models, intermediate is the unit operation models, and at the high level it's a flow sheet topology which we are trying to solve. So at the top level, the focus lies on the overall flow sheet topology involving sequencing unit modules. So how sequentially different uh, unit operations are arranged, initializing the flow sheet. So initially we have to start with some assumptions, with that what will be the output, identifying the recycle loops, and tier stream. This is a very important aspect, and we will see some more details on this. So for a very simple Williams and Otto flow sheet, which is a very simple, there is only one recycle stream is there. But when you look at the real plant, if you look at the refinery, there are several, thousands of the recycle streams are there, isn't it? So identifying these recycle streams, remember you have to solve this entire flow sheet. So when you wanted to solve this entire flow sheets in a sequential manner, remember this sequential word is extremely important when we are talking about the modular approach. We are trying to solve each of these units one after another in the same sequence, the way they are appearing in the flow sheet, isn't it? So identifying different loops, also identifying tier streams. So tier streams are nothing but we have to identify those streams. If we break the that particular stream, some of the recycle loops are broken down. So if you remove the recycle loop, then you can do the calculations in the sequential manner. So these tier streams are very important. We have to identify these tier streams, and we have to break the flow sheet at these tier streams. Based on that, the recycle loop is broken, and then we can do the calculations in a sequential manner. And finally, ensuring the convergence of mass and energy balance across the flow sheet is important. Okay, so this is what happens at the top level. So top level, we are performing these iterations to match the uh, energy balance and the mass balance in the flow sheet. What happens in the middle level? The middle level is concerned with the unit operation procedures and serves as a repository uh, of unit models. So when we are saying repository of the unit model, what it means is models with respect to individual units are solved separately. In fact, if you look at most of these plant designing, uh, the large scale plant designing, this is done mostly using the modular approach. You try to simulate each of these individual unit operations one by one in a sequential manner, isn't it? So repository of the unit models are there, then each solved with the specialized calculation procedures depending on what input are there and what output you are desiring. Inputs from the top level, including the input streams and parameters, are provided to each unit. So remember, output of each unit is given as a input to the next unit which is there in the sequence, in the um, uh, topology, in the flow sheet topology, isn't it? So you can see that there is a back and forth information transfer is occurring between the middle level and the top level. So inputs from the top level, including the input streams and the parameters, are provided to each unit, and outputs from the units are fed back to the top level once the unit calculations are completed. So once the unit calculations are completed, these output values again we feed to the top level, and then top level is again transferring that information to the next unit which is there in the sequence. So this level encompasses separators, reactors, transfer units, and other units those are present in the uh, flow sheet. Finally, the last level is a lowest level is nothing but the physical property models. So physical property models, these include basically thermodynamic models for phase equilibria, enthalpy, entropy, density calculation, etc. These models are frequently accessed by unit operation procedures as well as both top level, isn't it? So middle level as well as top level, both the levels are accessing these physical property models, isn't it, for flowsheet initialization and stream calculations. So each level operates largely independently with minimal communication between them. This streamlined approach allows the simulator to focus on one task at a time, enhancing the efficiency and clarity in the simulation process. Again, The flow sheet topology involves identifying recycle loop and tier streams for the unit sequencing. This is very, very important, primarily because uh, so see, you wanted to minimize the number of tier streams. So if you minimize the number of tier streams, then your calculation becomes very easy, isn't it? And also your convergence improves. In this analysis, the selection of tier streams plays a pivotal role, with the reactor feed frequently chosen due to its significance in the overall process dynamics. Okay, so selecting the tier streams is very, very important. Very often we select the input to the reactor as a tier stream, and that is what we have seen in the previous case. Also, you can see that when I am saying that we are assuming the inlet concentration of the uh, uh, different components in the recycle stream, these two are known. So clearly the inlet to the reactor is what we are considering as a tier stream, isn't it? So we are breaking this loop here, we are breaking this loop here somewhere, and that is why we could able to do the calculation sequentially in a forward direction, isn't it? So when identifying the tier streams, a critical consideration is selecting those capable of breaking all recycle loops, thereby facilitating smoother convergence. Addressing the specific challenge of recycle convergence involves considering a more focused fixed point relation x equals to gx, where x is represents the estimated tier stream flow rate vector and gx denotes the corresponding calculated stream flow rate vector. So what it is? So this particular point saying is what we are starting with the assumed value of x, we are starting with the assumed values of the concentration of different components which are coming as a recycle stream to the reactor, isn't it? And then again after the splitter we are again calculating these values. So these calculated values are nothing but what, gx, and this should match whatever we have assumed and whatever we are getting after performing the calculation as a input, this should match. And if these are not matching, we have to perform this calculation iteratively for several iterations till these are matching. So keeping tier streams minimal and ensuring they don't adversely interact during the convergence offers computational advantage. This is also very, very important um, point. So convergence depends on the tier stream. So clearly minimizing the number of tier streams and selecting the most reasonable tier streams is very, very important. Okay. So as I said, when we wanted to solve this flow sheet which is given by Williams and Otto, what we have to do, we have to break this recycle loop, isn't it? So our tier stream is the input to the reactor, isn't it? Once we have done that, then this loop is broken. So clearly now we are solving it in a sequential manner, isn't it? So that is what is represented in this particular slide. So you can see that we have broken the recycle loop here. Okay. So for this given flow sheet, the different steps involved are these: identification of the tier stream. So solving the Williams auto flow sheet begins with identifying the streams that break all recycle loops, isn't it? Remember our aim is what we want. So see, ultimately why this tier stream is coming into the picture, what this tier stream actually mean. Tier stream is nothing but we wanted to break the particular stream, and because of that if I am eliminating the recycle, that is what is called as a tier stream. So if I eliminate this recycle, then I can do the calculations in sequential manner. So that is why identifying these tier streams is very, very important. So in this particular case only one tier stream is there, isn't it? But if you look at the complex flow sheet, you will have multiple choices, isn't it? It's very, very uh, it is in fact combinatorial problem to find out the number of tier streams. Okay, that also we will discuss towards the end. Okay. So the choice of tier stream is flexible since there is only one recycle loop, allowing any stream within it to serve as a tier stream. Conventionally, the reactor inlet stream is selected as the tier stream for the process. Okay. So unit once this identification of the tier stream, that is the first step, then unit solution processes. After that what we are going to do, units within the flow sheet such as reactor, heat exchangers, decanter, distillation column, and splitter are solved following the flowsheet topology table. So whatever the flowsheet topology is there, how sequentially the units are arranged, this flowsheet topology which we are saying, this is also very important term here. In this case we can visually see in a Williams and Otto flowsheet, we can see different unit operations sequentially, but when we look at a complex flow sheet where there are a lot of recycles are there, in that case partitioning this entire topology into different groups is very important, and these individual groups are then solved. Okay, so that also we will see as we go ahead. So this process involves computing the output streams of each unit based on specified inputs and parameters. So module input specifications in this case are ensuring the proper specification of the inputs is crucial for maintaining the simulation integrity in each module of the modular mode. So depending on what inputs you are giving to each of these units, you will get the output. So clearly specifying the input parameters is very important here. The key parameters for the Williams auto flow sheet includes feed flow rates, then reactor volume and splitter purge fraction. These are the different inputs we have to specify, and based on that you can perform all the calculations. And once you do the calculations, then you are going to cross check all these terms one more time. Okay. So problem initialization entails making initial guesses for parameters like flow rates. Remember, that is what I said. Initial flow rates in the recycle stream that you have to assume, followed by iterative evaluation of the calculated values. Again you are going to calculate these flow rates in the recycle at the end, and then you have to perform the matching of that iteratively. Executing unit sequences starting from the reactor determines input streams for each unit, driving flowsheet convergence. So we can execute the simulation of individual units one after another, and finally we will be looking at the convergence of the all the units. Okay. So flowsheet convergence, when we are saying, when we are saying the flowsheet convergence, means whatever the assumed values we had in the starting equipment, that should match with respect to the recycled values we are getting. So once that is matching, then we are saying that the flowsheet is converged. So flowsheet convergence in the modular mode is typically framed as a fixed point equation, iteratively determining the output stream values for the convergence. Multiple passes through the flowsheet may be necessary to ensure the simulation accuracy and efficiency. So the recycle convergence algorithm plays a vital role in achieving the overall solution accuracy. The same thing which I am discussing here, that you get the output, match with the assumed input, and then you iteratively do this procedure till it is matching. That is what is called as flowsheet convergence. The final point is process demonstration. Solving the Williams auto flowsheet in modular mode showcases a systematic approach to analyzing and integrating individual units. So what we have seen is, if you solve these one after another, you can see that in fact we can match the input to the output. Now let's look at, so far we were discussing about the modular approach. Remember, we said that there are two approaches for solving the process flow sheet. Another approach is a equation oriented mode. So in equation oriented mode, what we are doing is, remember all the equations we have written for the individual units, isn't it? All these equations, in a modular approach we were solving the equations corresponding to each unit one by one, sequential manner. Now in a equation oriented mode, what we are doing is, we are solving all these equations simultaneously. That is what the equation oriented mode is. So equation oriented process simulation, the focus lies in solving flowsheet equations simultaneously. Departing from the modular approach, it involves combining all process equations and variables into a unified system for simulation for simultaneous solution. The structure of the equation oriented mode emphasizes integrating unit operations, physical property models and flowsheet topology into a comprehensive set of equations. So you can see that in a equation oriented mode, all these equations, including property, including the different unit operations, and also the flowsheet topology with respect to all, including the recycle and all these equations are solved together in a simultaneous manner. So equation oriented simulations are adept at managing large systems of equation with sparse structure. This word sparse is very, very important here. Why? Because if your equations are not sparse and they are involving several variables, in that case your equations have large amount of non-linearity, and solving such complex non-linear equation by using the non-linear equation solvers is going to be difficult, and is going to it may diverge also sometimes. So that then it depends on how uh, how good a initial guess is given to such non-linear equation solvers is, isn't it? So it depends on several factors. So but if your equations are sparse, in that case only few variables are associated with each of these equations. Clearly the equations are not that complex and you can solve these equations easily. So only a fraction of variables are involved whenever we are having a sparse representation. In that case only a fraction of variables are involved in each equation, optimizing convergence speed compared to the modular approach. So in that case you will see that the equation oriented approach is going to give you a much faster and much comprehensive solution compared to a modular approach. So despite a faster convergence and more efficient solution, equation oriented simulators necessitates careful initialization and problem specific strategies for successful resolution. As I said, simultaneous solving of flowsheet equations requires a robust large scale nonlinear equation solver and meticulous attention to problem setup for convergence. So what initial values you are giving, what nonlinear equation solver you are using, it the solution depends on these in a large extent. So initialization in the equation oriented mode is a problem specific and may entail grouping equations into a modular structure to facilitate successful resolution. Very in some cases whenever you have uh, a large number of equations are there, in such cases you sometimes you group these equations also in a modular approach, similar to a modular approach. Okay. So now this is what the all these set of equations are there for equation oriented approach. Remember in this case in this particular slide you can see that I have shown the equations for the reactors. These are the equations with respect to reactors. In addition to that we will have the equations for the kinetic uh, uh, this rate constant calculations, isn't it? So those equations I have not shown here, but even we will have equations for k1, k2, k3. These are the equations with respect to the heat exchanger. These are the equations with respect to the decanter. Then these are the equations with respect to the distillation column, and then finally again in addition to that these are the equations with respect to the splitter. And all these equations we have to solve in addition to the property calculations, and based on that uh, uh, you can see that all these equations are non-linear. So clearly a non-linear uh, solvers which can obtain the solution of these equations one has to employ. So the structure of the equations impacts the efficiency of the solution process. Typically each equation involves only a few variables, usually 2 or 3, emphasizing their sparse nature. Exploiting the problem structure at the equation level allows for specifying the degree of freedom. So knowing the degree of freedom is also very, very important here. Otherwise you end up with getting no solution at all. If the degree of freedom so see in this case you are solving large number of equations together, so calculating the degree of freedom is also very important here. If your degree of freedom is not correct, and if you are giving more number of equations than the number of variables, you end up with getting erroneous solutions or no solutions. Okay. So methods for solving the non-linear equation. Remember I said that all these equations are non-linear in nature. So typically if you look at all these solvers which are employed in several process simulation softwares like Aspen, HYSYS, etc., isn't it? So these are Aspen, HYSYS and all these are based on the modular approach, but also there are some softwares which can solve the equation oriented uh, formulation also. So in all such solvers you will see that the workhorse for those solvers is a Newton-Raphson method. So we will discuss that. So methods for solving the non-linear equations play a crucial role in process simulation. particularly in handling the complex systems where linear approximations are inadequate. Remember, we started initially when we have looked at the preliminary flow sheet designing. There we have used the linear balances, isn't it? We have linearized all our equations, isn't it? But those linearization is going to give you only the approximate solution. Once that initial part is done, in between you wanted to get the more accurate solution. So more accurate solution you can get by solving the non-linear equations. So non-linear equation solving techniques are essential for achieving convergence in process flowsheet simulations and optimizing the system performance. These non-linear equations have a general form like this: f of x equals to 0. So this is kind of these equations will be kind of equations for root finding. So f of x equals to 0, I wanted to find out the values of x for which f of x becoming 0. So this is kind of solving the equations where you are trying to find out the values of x which are satisfying all these equations. So it is in a way is nothing but root finding. A typical solvers used for solving such problems is a Newton-Raphson. So Newton-Raphson method, if you look at, it has a form like this. So this is for a root finding. So xk plus 1 is given as xk minus f of xk divided by f dash xk. So here you can see that f of xk is the function value at the kth iteration. F dash xk is the derivative value of the function at kth iteration, and based on that we can find out what will be the value of x at k plus 1th iteration, isn't it? So you can see that this particular Newton-Raphson method is for the root finding, but there is something called as a Newton's method which is used for the optimization. So when we are using the Newton's method, in that case the same equation is modified, and in that case the equation becomes xk plus 1 is given as xk minus f dash xk divided by f double dash xk. So you can see that there the denominator will be a Hessian matrix, whereas the numerator will be Jacobian. Okay, so in this case now the denominator is a Jacobian matrix. Okay, so in addition to this solving f of x equals to 0, sometimes we also wanted to solve at a fixed form. Fixed point form is what? Basically you are trying to match your output to the assumed output. So in a way x is given to the g of x. So depending on what type of equations you are solving, sometimes you can select a Newton-Raphson method or some other solvers also. So Newton-Raphson method stands out as the most utilized approach. In process simulation, it serves as the foundational algorithm. So you can see that all these solvers used are some way or the other derivative of the Newton-Raphson method. For the equation oriented mode, and finds frequent application in solving equations for unit operations. Additionally, quasi-Newton or Broyden methods are also used in this context. Okay. The next approach is the fixed order fixed point method. So when we are trying to match our output to the assumed input, these approaches do not rely on derivative information. So very often our equations are, so see, when we are trying to match x equals to gx, this is kind of whenever we are trying to look at what will be the concentration of different components in the recycle, isn't it? So in such cases finding the derivative is not easy. So in such cases, remember Newton's method here, Newton's method or all the methods which are derived from the Newton's method, they are based on derivatives. But in the other case where we are trying to match our output with the assumed input to the reactor in the recycle stream, in such cases finding the derivative is not easy, and in such in order to satisfy such requirements, one has to use the methods which do not require the derivative, and one such method is shown here. So secant method is shown. So secant method is kind of extended version of the Newton-Raphson method itself. The only difference here is this derivative we have obtained as a difference equation here. You can see that f dash xk, instead of f dash xk, now we have written here it as f xb minus f xa divided by xb minus xa. So this is a difference equation we have written. Okay, so clearly we do not require a derivative here, only we require a function value at 2 points a and b, and based on that we can calculate the difference, and that difference we can use as a derivative, and then we can find out the new value of the x, isn't it? And once we get the new value of x, we are going to eliminate some of the search space. So if you look at the secant method basically based on not just the concept of the Newton-Raphson, but it also based on the concept of eliminating the search space. So it eliminates the search space based on what value of x new we are getting, and then we are going to look at x new value, whether this x new value and whether this x new value is between xa and xb. If it is between xa and xb, in that case the subspace between xa and x new, that will be eliminated, and our new subspace will become x new to xb, isn't it? So clearly you can see that as we progresses for different iteration, you will see that even the secant method will approach to the global optimum or a desired solution. Okay, if you take the example of Newton-Raphson method, as remember I said that sometimes such these derivative based methods are really tricky. So you can see that this Newton-Raphson method sometimes it may diverge also. If you select your initial value, remember this particular method, both these methods are requiring the initial values. So depending on what initial values you are starting with, based on that sometimes your algorithm may diverge also. Now let's move to the last part of this session, and this is very very important: recycle, partitioning and tiering. This is extremely important when you are trying to solve the process flow sheet by using the modular approach. So recycle, partitioning and tiering algorithms are essential in modular process simulation for handling recycle streams and ensuring the convergence in the flow sheet calculation. Okay, so these methods are particularly important in systems with recycle loops where mass and energy balances need to be closed effectively. Now, in order to understand, remember so far we were looking at a very simple flow sheet, Williams and Otto. Let's look at slightly more complicated flow sheet where there are several recycling streams are there. So you will see this is the new flow sheet. This flow sheet is given by Leslie Emmy in his book Computer Aided Process Plant Design. So you can see that now making the decision is not easy. Can you find out how many recycle streams are here just by visual inspection in one go? It is not possible. It is really difficult to find out the number of recycle streams, and also it is difficult to find out what will be the different tiering streams, and not just that, what sequence I should follow in a modular approach for calculation. Finding these things are not easy when I am having a complicated flow sheet of the given plant, isn't it? So this is what we are trying to understand here. So you can see that recycle, partitioning and tiering algorithms are essential. These methods are particularly important in systems with recycle loops where mass and energy balance need to be closed effectively. In the process flowsheet from the literature, the same which I have shown, you can see that there are different units are like A, B, C, D and E are there, form a recycle loop. So you can see that if I go in this particular thing, you can see that A, B, C, D and E, these are forming a recycle loop. So I can clearly say that there is a recycling is happening here. In addition to that, I can consider even, so see, the output from the C is going to F and then it is going to G and it is again coming back. So I can take even F and G into the consideration. So A, B, C, D, A, B, C, D, E, F, G, this can be considered as a one group here, isn't it? So I can go in a sequential manner in solving these groups, these units here, isn't it? But how about the remaining part? This part I can visualize easily, but visualizing the other parts is not that easy. So such groups like A, B, C, D, E, F, G units that need to be solved together. Okay, so you can see that we have identified that A, B, C, D, E from the recycle loop and must be computed together, isn't it? Clearly because they are part of the same loop. Similarly, F and G we can connect with them, isn't it? So finding such groups which need to be solved together, that is what is called as partition. So this entire group is called as a partition and this entire procedure is called as partitioning. So whenever I am having a complicated flow sheet, the first step in a modular approach which we have to do is we have to partition this particular flow sheet into different partitions. In each of these partitions we will have a group of different units, and this group of different units has to be solved separately. Okay, so the order in which these partitions must be solved is known as precedence ordering. So this is also important, in which order all these partitions has to be solved, isn't it? So in this case this is one partition, isn't it? And again, in addition to this one partition, there will be several other groups will be there. In what sequence these groups should be solved, isn't it? So that is called as precedence ordering. And the last point here is, while the grouping of the units into partitions is unique, the ordering may be depending on the specific flow sheet. So what we are trying to say is, for a given process flow sheet, you will see that your partition groups will be unique. If you follow the procedure, you will get the unique partition groups, but which order should be followed, that may not come unique. Okay, that may depend on what you are starting with. Okay, so now let us do the partitioning and obtaining the tier streams for this particular complicated, slightly more complicated process flow sheet. So the first task we are going to do is the recycle partitioning. So a simple algorithm exists to find the partitions and precedence ordering in any given flow sheet. This algorithm is illustrated on the given flow sheet here. So you can see that the first step is arbitrarily select any unit. Let's say unit I we have selected. So unit I is where? Unit I is here. This unit I have selected arbitrarily. I could have selected any other unit, isn't it? Then after that, what we do is we are putting that unit in the list 1. Put it in the list 1. So list 1 is now comprised of unit 1. Okay. So for uh, unit 1, for unit I, we trace its output stream. So we look at this unit I, we try to find out what are the output streams it is having. So in this case, you can see that this is one output stream from unit I, this is also another output stream from unit I. So you can see that if I take this output stream, then I try to connect all the output streams. So you can see that for unit I, we trace its output streams, adding each new unit to our list until we encounter a repetition or reach a dead end with no further output. So we continue adding individual units based on if there is a output stream present, isn't it? And we continue till we come back to the original unit or a repeating unit, or there is a dead end. Tracing outputs. So if we are tracing the outputs from I, we can go from I to J. You can see, if I look at from I to J, I can go, from J to K, I can go, from K to L, I can go, from L to M, I can go, from M to N, I will go, from N, I will come back again to L, isn't it? So now there is a repeat unit. Yeah, from L, I have gone to M, N, and then again come back to L. Okay, so we have to continue till there is a repetition. Okay, so in this case, you can see that from I, we will go to J, J to K, K to L, K to M, L to M, and M to N, and finally L. So now you can see that this L and this unit L both are repeating. So when we are identifying a repetition, we group the units in the loop and treat them as a single entity. So here L, M, N, these three units, we have to group them and we have to consider them as a single unit. Okay, so we can loop them, we can group them in a single unit, and that is represented by this bracket. So now you can see that after grouping this is what we have obtained. I, J, K, and this L, M, N, we have grouped them in a one unit. So that is why this curly bracket is there, isn't it? So this L, M, N, we have grouped as a single unit. Now let's look at continue the tracing the output. Okay, so after that, again we can consider the tracing the output. So you can see that from L, I can go to O. Remember, I reach to L, and then from I can go to O, then I can go to P, and from P I can go to K, and K is what I have started with, isn't it? So in this case, we will go to OPK, and now there is a repetition between K and K here. So again, we have to group all these units which are present between these repetitions. So that is what we have done. So we have grouped them, K, L, M, and OP, we have grouped them in one unit. Again, we can go ahead, isn't it? So this group, we are now considering a single entity. This entire group we are considering a single entity. So now you can see that again in this case, from here you can see that we can again go from here M to S, Q, R, J. This is what we can go, isn't this entire unit we have clubbed into one unit. Now we can, if we club them as a one unit, there is again output which is going to S. From S we are going to Q, from Q we are going to R, and from R we are going to J, isn't it? So we can put that also here. So S, Q, R, J we have put here. Now J is getting common here, J is getting repeated, so again we can group them together, so that becomes J, K, L, M, N, O, P, Q, uh, uh, P, Q, R, J, isn't it? PSQRJ. This is what we have, entire group we have obtained. Now once we have grouped that, then there is no output going after this. After once we have grouped this entire, when we have grouped this entire term here, now there is no output going. Output going to a dead end, like byproduct, like created hydrocarbon product, etc. It is going to a dead end. There is no output going to a unit from this. If I look at this particular, if I look at this particular part, if I look at this particular part, you can see that there is no output going to a other unit, isn't it? Correct. So this entire thing is one group, isn't it? So here you can see that now this entire thing we have made one group. After that, the next step is we have to see, remember I we have started, isn't it? I we have started, we said I is going to J, isn't it? And that was one output we have seen, isn't it? I is going to J, but I can have another output to other unit also, isn't it? Correct. But I is going to Q, but Q I have already included now here. So there is no output going from I, so this becomes a dead end. We don't have to go ahead with that. So what we have to do here is, once we have obtained this entire group we are going to copy in the list 2, and whatever remaining I, that will again put it in the list 1 itself. In the list 1 we are again going to see whether I is having another output going to other units. In this case, from I we are not going to any other new units at all, so therefore this is a dead end. Okay, so this I again go back to the list 1 and it remains at the top here. Okay, now let's select the another unit. Now let's select the another unit arbitrarily, maybe let's say F, unit F we have selected. So unit F we have selected, isn't it? So from F we have to see what is the output. So let's say from F the output is H, isn't it? If I go from F to H, and H to I can go, isn't it? But I is already used in this one group. So if I go from F to H, there is a dead end. Remember, this stream is coming in, it is not an output. Only I have to look at whether there is an output stream or not. So from F it is going to H, and then there is a dead end. So I will have another group from F to H. That's it. So that is what we have obtained here. See, we are starting from the F, then it becomes FH, isn't it? After that there is a dead end. So this FH also is there. So remember here F to H is going, so H is going to come back to the list 2. So H we have taken again, copied to a list 2, and it becomes at the top, isn't it? So H comes here, and again we have to see whether F is having another output or not. Remember, we have selected one output, we have selected this output for the F, but F is also having this output. This particular direction we have not explored. So now in list 1 I will have F, and I am going to explore this direction. So we will have FG, we will have FG, C, D, E, A, B, isn't it? And again it is coming back to C. Correct. So that is what we are having in the next thing. We are starting with F, we are going to F, from F it is going to G, C, D, E, A, B, and finally it is coming to C, but C is getting common here, so we have to group that. C, D, E, A, B will be grouped here. Again after this group there is a F which is output. So this entire thing which is I have clubbed, so from this I can go to F again, isn't it? So then there will be F also at the end. So C, D, E, A, B, and F is there, and F is common here. So clearly we have to take F, G, C, D, E, A, B as one single group. Now all these units we have counted. Now this particular group I have to take as a this particular group I have to take in the starting here in the list 2. So what we will have in the list 2 now? F, G, C, D, E, A, B as one group, H separately, I separately, and the last group will be J, K, L, M, N, O, P, S, Q, R. So now this particular list is very important. Why? Because now it is giving us that how we should group different units. So we should group unit F, G, C, D, E, A, B as one unit, and we have to solve the material and energy balance, all these equations we have to solve for this group first. Then the output from this group will be given as a input to the unit H. We will be solving unit H. From unit H we will be giving the output to unit I. We will be solving unit I, and once we get the output for unit I, then we will give it as a input to this entire group J, K, L, M, N, O, P, Q, O, P, S, Q, R, and in this manner this entire flow sheet one has to solve. So clearly this is something called as partitioning. So here we have partitioned the all the units into different groups. You can see that this is the first group, then second, third, and fourth. There are four groups we have obtained, isn't it? So we repeat this process until all units are accounted for in either list 1 and list 2. Finally the list 2 represents our partitions in precedence order. So this is in the precedence order. This is how we have to process our material and energy balance calculations. This meticulous approach ensures the systematic breakdown of the flow sheet, facilitating the efficient solution strategies for complex process systems. So this is about the recycling, partitioning, and the last topic now remaining is a recycle tiering. Remember, once we have found out the partitioning, we have only obtained the information that how we should solve the material and energy balancing sequentially. But one more information is required. Which stream should be used as a tiering stream so that these recycle loops are separated, isn't it? Recycle loops are broken down. Okay, so tiering is a crucial step in the process of solving partitions containing multiple units in a flow sheet. It involves strategically selecting tier streams to break recycle loops and facilitate convergence in the process simulations. The tiering process aims to identify key streams that can be removed temporarily from the system, and because of that solution of the interconnected units and improve the convergence behavior of the simulation. Once the approach One approach to tiering involves analyzing the flow sheet to determine the most effective tier streams that can efficiently break the recycle loops without compromising the accuracy of the solution. The tiering process is essential for handling complex recycle structures and ensuring the convergence of iterative solution methods in process simulations. By breaking recycle loops strategically, engineers can simplify the solution process and achieve consistent and reliable results in flowsheet calculations. Okay, so what we are trying to say here? We are trying to say here is that for a given flow sheet, we have to first find out the tiering streams. Again, we have to minimize their numbers. If you minimize the number of these tiering streams, our calculation becomes easy, and also the convergence becomes easy. Okay, the last point here is the advanced tiering techniques such as integer programming formulations can be used for optimization and can be employed to systematically select tier streams and optimize the convergence behavior of the simulation process. So this part we are going to see. So you will see that once we have obtained different recycle streams, out of this recycle, by considering this information about this recycle streams, we can find out the tier streams, and these tier streams we can find out by formulating the set cover problem. This set cover problem is a combinatorial problem, and this combinatorial problem can be solved by using the integer programming. And once we solve this integer programming problem, we get the optimized values of optimized number of the tiering streams. This we can use, and based on that we can break the entire flow sheet and perform the calculations in a sequential manner. So let's look at for the same example. So in the same example you can see that remember we have done the partitioning. So this is the first group, second, third, and this is the last group. So we are going to perform the tiering for the last group, JK, LMN, OPS, QR. So these are the units which are there. So all other units we have removed from this flow sheet. So from this flow sheet only this JK, IJK, LMN, SRQ, all these units are retained and all other units are removed. And also the outlet streams and inlet streams which are not coming from the equipment or not going to any other unit, these are also removed. So with that you can see that our process flow sheet for only this partition JK, OPS, QR becomes like this. So I have separated all other parts, and the streams input and the output streams which are not going to any unit, these are also removed. So this is the process flow sheet which we have obtained. Now in this process flow sheet, again those units which are having only single input and single output, these are also omitted. So that is what we have done. See, here Q is having single input, single output, so that is also omitted. So this is the resultant flow sheet which we have obtained after removing uh, the units which are already not there in this particular partition. And also we have removed the units which are having single input and single output, like the unit Q where there is a single input and there is a single output. So that is also we have eliminated from here. So our resultant flow sheet becomes like this. Now this resultant flow sheet again can be represented in a simplified form like this. So where you can see that this individual lines now represented as streams, and these are represented with numbers. So for instance, you can see that from S to K this entire line is considered as one stream. So from S to K this particular stream is represented by a number 8. So in a similar manner, all the streams are represented with numbers like 1 2 3 4 5 6 7 8. Now in this particular figure we wanted to find out how many recycle loops are present, and based on this recycle loop then we have to find out which stream will be the best stream for tier. So now in this case again a simple algorithm is there. We start with any unit in the partition. For example, let's say unit K. We can take a unit K. So from unit K then we have to go in the forward direction. So from K the only output is going to L, and from L it is going to M, and again from M it is coming back to L. So you can see that K to L, L to M, and M to L, and the in between what is the stream number that is represented here. So you can see that from K to L the stream is 1. So from K to L the stream is 1, and from L to M the stream is 2, and from M to L it is coming back, the stream is 3. So that is what is represented here. So clearly um, uh, this particular unit is getting repeated here. So this is a loop. Clearly this is a loop. So we can represent this loop in terms of the stream as 2 3. So the list 3, now we are making another third list which is counting the loops here. So we are having the loop between 2 and 3. So that is represented in the curly bracket here. 2 to 3 is a loop. Okay. So start with the unit just before. Okay, so we have looped this unit uh, L here, isn't it? So this 2 to 3 we have looped it, isn't it? So now again we are starting with the unit before the repeating unit. So L is the repeating unit, so we have to start with K. So again we have to start with K and see whether there is a any other output is there. Trace the path from K to unit L and then to unit M. Okay, so in this case you can see that if you go from here L to M, now you can see that here from M there is another path is there, isn't it? From M we can go to S, and from S it can go to K, isn't it? So that is what is represented in the next line. So trace the path from unit K to unit L, then to unit M, and then back to unit L, and finally to unit S and K. So it is going from K to L, L to M, and from M to L it is going, but again from M it is going to S, and from S it is going to K, isn't it? So there is a loop between these two. So K unit is same, so there is a definitely one more loop here. So this also we can represented in a list 3. So list 3 I will have what are the streams here in between 1 2 3 7 and 8. So that becomes 1 2 7 and 8, isn't it? So 2 3 we have done. So 1 2 7 and 8 becomes the second loop here. So note that the unit K repeats, and the streams 1 2 7 8 connecting the appearances of unit K are added to the list of the loops. So that becomes 1 2 7 8. Now remember, in this case again, upon returning to S and exploring the alternate path from it, none are found. So what it means is, you can see here at the S we have reached, isn't it, in the second loop, but from S there is no alternate path, there is no outgoing here. So yes, we cannot explore, but you look at the L, we can explore. From L there is a alternate path which is going to O, isn't it? So note that L repeats, and the two streams 2 and 3 connecting the two appearances of unit L are placed on the list of. So here you can see that 1278 we have included here. Upon returning to S and exploring the alternate paths from it, none are found. Revisiting unit M also yields no further exploration path. So if we again go back to M here, from M there is only one outgoing which we have already explored. There is no alternate outgoing from M. However, retracing the steps to L reveals an additional path as follows. So we can, so see, these two paths we have already found out. Remember, from L, M, L, this is one loop. Then from M, then there is a 7, 8, and then K, isn't it? And from L is also there is an alternate route. You can see from L, I can go to O, and O to again I can come back to K, isn't it? So this is what is represented here. So L to O and O to K, and the stream name is represented here 4 and 5. So we can see that here in this case one more loop will come into the picture, and that will become what? 1 4 5, 1 4 5. That is what the third loop is. Now there is one more loop is possible at the O. So you can see that O there is two outputs are there. One is going to K and another is going back to S. So there is one more loop is possible here from O. So we can have one more loop represented here, which will be from O it is going to S, and from S to it is going to K, and their individual stream numbers are also represented 6 and 8. So we will have a loop like 1 4 6 8, 1 4 6 8. So these are the four loops which are possible. So you can see that upon returning to S, then to O, followed by L, and finally to K, no alternate paths from these units were discovered. As we have returned to the initial unit on the list, our exploration concludes. So there is no units remaining, resulting in four loops in the partition. So these are the four loops are there. Now with respect to these four loops, we have to find out the tier streams. So these loops are recorded in a loop incidence array as depicted in table. So you can see that all these four loops are represented in the loop incidence array. So this is the loop incidence array. So first loop is what? Between 2 and 3. So these particular boxes are marked by X here, but I could have used 1 and 0. So I could have used 1 for X, and all blank spaces I could have used 0, and that is what the representation used in solving the combinatorial set covering problem to find out the minimum number of tiers. Okay, so in this case, once this loop incidence array is found based on the loops we have obtained, then we have to solve a combinatorial set covering problem. And in this, what we have to minimize is we have to minimize the count of tier strings. And once we solve this particular problem, then we have to go ahead with the calculations. Okay, so solving this set covering problem is not easy. It's a combinatorial problem. It is exponential time complex. Typically for a small number of variables, you can solve using the deterministic methods. Usually people use the heuristic methods. In this case you can see that integer programming methods one has to use to solve. And once you get the number of tier streams, then you can perform the entire calculation. So we employ the reduction properties outlined above for the matrix analysis, and then this entire matrix which we have obtained is very important for solving this set covering problem. And this particular problem is already solved in the book for a very simple case, so we will not go ahead with that. So we stop here, and in the next session we will again start with the optimization. Thank you so much.